Welcome to this video. I am Mrs. V. Indirakumari, Assistant Professor, Department of Chemistry, Trinity College for Women, Namakkal. Today we are going to see about photochemistry. Photochemistry is the study of interaction of electromagnetic radiation with matter resulting into a physical change or into a chemical change. Primary process of photochemistry. One molecule is excited into an electronegatively excited state by the absorption of photons. It can undergo a number of different primary processes: photochemical process and photophysical process. Photochemical processes are those in which the excited species dissociated or isomers are rearranged or react with the another molecules. Photophysical process includes radioactive transition in which the excited molecules emit light in the form of fluorescence and phosphorescence and return to the ground state, and the intramolecular non-radioactive transition with some or in the energy of the absorbed photons is ultimately converted to heat. Three laws of studied by the absorption of light. First one, Lambert law, Beer law, and then Stark-Einstein law. First one, Lambert law. The law states that the decrease in the intensity of monochromatic light with the thickness of the absorbing medium proportion to the intensity of incident light, that is minus di divided by dx, directly proportional to I. That is eliminated to directly proportional. We put a proportionality constant k. I equal to I naught e power minus kx. What is I means intensity of transmitted light. I naught is intensity of incident light. K is the absorption coefficient. Beer's law. It states that a decrease in the intensity of monochromatic light with the thickness of the solution is not only the proportional to the intensity of incident light but also concentration of the solution. Mathematical formulation of minus di divided by dx directly proportional to IC. That's eliminated to directly proportional. We put the proportionality constant to epsilon. Epsilon is the molar absorption coefficient or molar extension coefficient. Groth-Draper law. Only the light which absorbed by a molecule can be effective in producing a photochemical change in a molecule. Stark-Einstein law. The second law of photochemical reaction. It states for each proton light absorbed by a chemical system, only one molecule is activated for a photochemical reaction. The energy absorbed by one molecule of reacting molecules is given by E equal to N into HV. This energy is called as 1 Einstein. In numerical values of Einstein, in CGS unit, Einstein E equal to 2.86 divided by lambda, that is calorie per mole, or 2.86 into 10 to the power minus 5 or plus 5 divided by lambda Kelvin calorie per mole. In SI unit, E equal to 0.1197 divided by lambda joule per mole, or 11.97 into 10 to the power minus 5 divided by lambda Kelvin joule per mole. Quantum efficiency. Quantum efficiency is denoted by pi. Pi, which is equal to number of molecules reacting in the given time divided by number of quanta of light absorbed in the same time. But experimentally, pi, which is equal to rate of chemical reaction divided by quanta absorbed per second. Quantum yield is denoted by the photolysis process. The photolysis of chlorine and the hydrogen, pi value of hydrogen chlorine can be high value of 1 million. Chlorine is reacted to photochemical reaction, that is absorbed in HNO radiation to form 2 chlorine atom. Again, 1 chlorine atom reacted to the hydrogen, 2 molecules of hydrogen to form HCl and 1 molecules of hydrogen atom. The hydrogen atom is reacted with the molecules of chlorine to form hydrogen chlorine and hydrogen atom. But the same time, photolysis of bromine with reacted with the hydrogen, pi value, pi means quantum yield value is very low, that is 0.01 value. Bromine reacted with the hydrogen, that is means photolysis to form 2 bromine. Again, the bromine atom to reacted to hydrogen molecule to form hydrogen bromide and hydrogen. Hydrogen is the endothermic reaction. And previously, chlorine react with the hydrogen to form hydrogen molecule, that is exothermic reaction. Exo means evaluation of heat, endo means absorption of heat. Luminescence. Luminescence means evaluation of heat that is produced in a light energy. Glow produced in the body by the method other than the action of heat, that is the production of cold light, is called luminescence. It is of three types: chemiluminescence, first one, fluorescence and phosphorescence. Chemiluminescence, the emission of light in the chemical reaction at ordinary temperature, is called chemiluminescence. Example, light emitted by the glowworms. Fluorescence, certain substance when exposed to light or certain other radiations absorbed by the energy and then immediately start re-emit the energy. Such substances are called fluorescent substance, and the phenomenon is called fluorescence. Example, organic dyes such as kerosene, fluorescence, etc. The vapor of sodium and mercury iodine also the fluorescent substance. Phosphorescence, there are certain substances which continue to glow for some times even after external light is cut off. This phosphorescence is a slow fluorescence. Fluorescence and phosphorescence in the terms of excitation of electrons. Before they will be collide in the ground state, that is in a single state, they are in a pair. It is opposite signs. First one in the single state, the S1 is the pair of electrons at opposite signs, is the different orbitals. Then triplet state T1, the pair of electron with the parallel spin with a different orbital. The excited species can return to the ground state by the losing of all excess of energy by any one of the path shown by the Jablonski diagram. This is the Jablonski diagram, and the S0 is the singular state for the ground state, and they will be absorbing energy to form in the excited state, excited singular state S1 and S2. Here it will be loss of energy to return to the ground state, that is S2 to S1, that is internal conversion. Again it will be energy shifted to the another triplet state, that is inter-system crossing. Here the energy will be emitted S1 to S0 state, that is fluorescence, and T1 state to S0 state is phosphorescence. Jablonski diagram explanation. The first step is transition from higher excited singular state to the lower excited singular state S1. It is called internal conversion. It is a non-radiation process, occurs at less than 10 power minus 11 seconds. Now from S1 molecule return to the ground state by the following path. Path 1, molecule may lose rest or the energy loss and also to form a heat, and the complete path is non-radioactive. Path 2, molecule release energy in the form of light or UV radiation. This is called fluorescence. Path 3, some energy may lost or transfer from S1 state to T1 state from the heat. It is called inter-system crossing, ICS, that is ISC. The path is non-radioactive. Path 4, after ISC, inter-system crossing, the molecule may lose energy in the form of light is going from excited triplet state to form in the ground state. It is called phosphorescence. Photosensitizer reaction. An electronically excited molecule can transfer its energy to second species, which then undergo the photochemical process, even though it will not itself directly excited. Mercury acting the photosensitizer. Mercury with absorbing heat energy or light energy to form in mercury activation state. The mercury activated mercury react with the hydrogen to form mercury and to form of hydrogen. Chlorophyll acting as the photosensitizer. In the presence of carbon dioxide, they will be available in our atmosphere. It's react with the water, and in the absorbing the light energy in the presence of chlorophyll to produce in the carbohydrate and oxygen. Thank you for watching this video. See the next section. Thank you.